My name is Serkan Kalender. Me and Dr. Park are basically Servo scientists for Delta Tile. And the tuning tool, the firmware as well as the software, I wrote it. And on top of that, we have actually for more advanced users, a system identification and frequency response measurement or experimental body plots gathering software, which is called Servo Analyzer. But for the sake of basic training, we don't talk about it. But later on, I can arrange some time so that I can either give you a presentation or show the software. But essentially, for today, we're going to be talking about our tuning software. And before starting, I can tell you, for those of you who knows about our older generation controller, Turbo PMAC, there's a big difference in terms of speed, of course, much more powerful CPU. It uses floating point mathematics, which allows us actually to have a much more general control algorithm. Our standard control algorithm, I'll show you, on top of some other algorithms that built in the firmware, is capable of basically having like 3 notches. It has like a 7th order filter. It's quite general, so you can use it like pretty much 98-99% of your machines or axes, you can use it. On top of that, of course, there's one more thing. Everything is in C. So you can write a user-written servo. Like in the old gen, you could have write also open servo, what we call an open servo. Or you have to write your code, a compiled code, which has to be written in assembly, because it was using a digital signal processor. So here's the good part about it. You can write your own user-written code. It's really simple if you know C. And if you don't know C, there's something called MATLAB. The old times it was called Real-Time Workshop. Right now they changed the name. It is like MATLAB Coder. And you can easily select Power PMAC as a target. We also have tools for that. So let's say if you're more in like modeling and designing your control laws in MATLAB or Simulink, you can design your controller with a given plant model, separate the controller, generate the code for Power PMAC, and grab those files, put it in user routines, and you can run it. It's simple as it is. But almost always, the tuning, the standard servo algorithm will allow you to do lots of things. And we have, as I said, built-in algorithms such as simple PID. I'll start with that one. It's the basic PID structure. This is the simplest one of all. And you can see that there's proportional velocity feedback and velocity feedback into the integral loop, as well as standard velocity feedback. And we also have feed-forward terms, acceleration feed-forwards, velocity feed-forwards. This is the really standard basic algorithm that you can use. And almost all the case, you don't need to worry about this. This may be useful if you have, let's say, too many axes, and if you're starving your CPU. This is highly unlikely with Power PMAC. But for those of you who wants to use a simple PID without no filters, which means you don't have any dynamics, or you don't have high frequency unmodeled noise, so you can filter out, you can use this standard PID algorithm. So if we look at our tuning tool software, actually, I don't know if it can be clearly seen from there, but the main page comes up with the motors that you can select, which motor to tune. And we have tabs, which basically is a standard way of tuning starting for a brushless motors, for example. And if you're commutating it via Power PMAC, you would first start tuning the current loop. And then you will check to see if your current loop is running correct, or you can use open loop test to understand the dynamics of your machine. And you can actually see if you have resonances at really low frequencies with the open loop test also. And then the next step is what we call position loop auto-tuning. It's going to help you to tune the motors via estimation algorithms. And we have the position interactive tuning that you can see that we have all the gains. You can actually change it on the fly, look at their responses with multiple standard inputs. And later on, I'll talk about what a trajectory prefilter helps to you, as well as adaptive control setup and interactive filter setup. There's one more thing which is going to be in the next release, which we call is iterative learning control for cam and compensation tables. But that's something else. That's the last step. And if you look at the tool, all the time, it's going to show you what is the commutation status of the motor, which means that you don't need to go back to the IDE and look at if it's set up as a brushless motor, if it's commutated via PMAC. It's going to show you if it's commutated let's say for a brush motor, it's going to show you not available because it's not commutated at all. You cannot commutate it. But if it's a brushless motor, it's going to show you if it's phased or if it's not phased. And you can, in that case, you can easily phase the motor directly from the tuning software. So you don't need to go back and then issue a dollar sign for the motor. Also, you can enable closed loop. And here also, it's going to show you motor errors, if there's any errors, such as like pedal following errors, if you hit hardware or software limits. And it's going to also show you directly what type of motor is this. Independent means it's not in a gantry mode. It's going to also show you if you have a gantry setup motors, two motors, it's going to show you if it's a gantry follower or a leader. And it also shows you what type of servo algorithm it uses, such as like gantry cross-coupled control, adaptive control, standard control, simple PID control that I show you. It will also directly show you if you have filters implemented, such as like a notch. And I'll talk about later about the filter calculator and how the software tells you what type of filter is implemented, what frequencies, everything is stored. So that's the good part of it, so you don't need to worry about it. And it's going to also show some other extra windows over here, which is basically shows errors if there's any error. Let's say if you type something wrong, it's going to show you, okay, this is not a valid input. All the errors are going to show up in this error tab. Information window shows what software is doing to you. Also, it's going to show you if you implemented a filter, at what time, at what instance, so which are good, so you know everything about what's going on. And the output window shows which commands are sent from the software to Power PMAC. Okay? The debug window is for me, so you don't need to worry about that. And the warning windows shows the warnings. So as I said before, so the first step for a brushless motor, and if we want to commutate via Power PMAC, we have to tune the current loop. Essentially, we have 3 tabs over here. I'll talk about simple auto-tune later. Auto-tune current loop basically asks you to, for the design goals, such as what is the bandwidth and the damping ratio of the current loop. And you can select the excitation magnitude in terms of the maximum DAC and excitation time. And the test gain is basically just the proportional gain of the PI controller in the current loop. Essentially what it does is is a system identification routine. It does a step and tries to find out what is the resistance and the inductance of the, so it tries to estimate the electromechanical properties of the motor itself. And it's going to come up with the gains for you. And you can easily look at its response. The interactive tune, on the other hand, of course, after you come up with some auto-tune gains, you can easily fine-tune your gains by using this tab. So it allows you to look at different responses when you change the gains. Like a typical response, and if you look at its response, it's going to show a step in the, it's going to be a simple step move for the motor count loop, and it's going to give you information with regards to the statistics with regards to your control loop, such as the rise time, natural frequency, damping ratio, all those things, so that you can easily compare different set of gains. You can compare their responses quantitatively, of course. And after this step is done, you have to test if your you have to test to see how your system responds after the current loop is done for a brushless motor, or for a brush motor you have to look at its response. And we have several different type of steps. The most useful is what we call the step test. It's basically just applying a open loop command to the motor and see how it behaves. And you can also use a sinusoidal test for like different frequencies, as well as a sine sweep, but you have to be careful about this. With sine sweep and sinusoidal, your motor may drift, and these are also used for identification purposes. And you can, that's basically is going to be a good tool to understand the dynamics of open loop. And it's also really useful in terms of seeing if you have any resonances, if it's really at low frequencies. At high frequencies, you won't be able to see those. If you have a resonance flexibility in your system which is high, you won't see that. But if it's really low, you'll be able to tell it. After verification of the open loop, you can go to the auto-tuning. Essentially, the Advanced Auto-Tune tab is similar to current loop tuning. You ask for this, the user has to specify the desired performance, which is in terms of the bandwidth and the damping ratio. And you can select the amplifier type, and you'll see there's going to be 3 amplifier types, but actually what we are meaning is just to make users understand it simpler. So essentially we actually go for 2 different set of models, which is what we call torque modes and velocity modes. And again, the idea is similar. It does an auto-tune move. You will see it when you do it, and tries to identify the hardware gain, if it's a torque mode, and if it's a velocity mode, it's going to identify the hardware gain as well as the time constants. Also, you can ask for, you can change the excitation settings. These are typically the best set by using the open loop test. And you can ask for integral action, either soft or hard. You can ask the software to come up with the feed-forward gains for you, velocity and acceleration feed-forward gains. On top of that, if you don't have any idea about the desired performance, you can ask for auto-select bandwidths. So it's going to come up with some conservative bandwidths based on the estimation of your gain. Okay? If it's a high resolution, if it has a high resolution encoder, it's going to come up with a little bit more high bandwidth for you. And you can also ask the software to choose for you the sample periods, as well as if you can ask for the software to come up with also with a low pass filter. And typically we almost always use our standard servo algorithm. And here's the difference between what we had with a PID. So what you can see, so we have again our PID terms, proportional, integral, velocity feedback. Velocity feedback, you can also have a velocity feedback inside through the integrator, which actually in some cases which is useful so that you have a better response in terms of velocity. So they are different. Typically either you use this or the other one. And you will see we have also an acceleration feedback. In some cases this is really useful. Let's say, although it has to be used, in some cases you have really low frequency resonances. With XL feedback, you can actually make these low frequency resonances go a little bit higher frequency so that you can notch it out inside your servo. Otherwise, you won't be able to do it without decreasing your bandwidth. So that's how it's useful for. And on top of these, of course, we have feed-forward terms and acceleration feed-forwards, velocity feed-forwards, and we have friction feed-forward, which is a nonlinear compensation. And more importantly, these C, D, A, B polynomials, their filters are 7th order. Essentially, this allows us to implement like 3 notches if you have 3 resonances, or 7th order low pass filter if there's a need, or a combination of both. Also, we have an extra flexibility here. You can have a filter in the velocity feedback path. And by the way, this A, B, Z, especially D polynomial, also can be used to design what we call as a pole placement controller or 2 degree of freedom controller for more complex dynamical systems. And by the way, this is quite general, as you can see. And we can also talk about extra nonlinear compensation terms. We have a deadband compensation here. And we also have already built in a hysteresis control on the output of the servo. And typically, velocity feed-forwards, friction feed-forward is used for compensating for drive friction on your system, or column friction. So it's quite general. So this allows us to do lots of things, of course. And when we'll talk about filters, it's going to be much more clear. After the auto-tuning step is done, you can go to position loop interactive tuning, and you can actually use these standard test inputs, such as step, ramp, parabolic, trapezoidal, S-curve, sinusoidal. You can do a sine sweep to look at its frequency response, the closed loop frequency response. And you can also write your own user-defined motion to see how your tuning works. Most of the cases, you're going to be using step and parabolic. Step for basically looking at point-to-point move effectiveness of your control gains, and parabolic for your tracking performance. And parabolic is used typically for fine-tuning your feed-forward gains. And by the way, there are, of course, for each move, you can kill the motor after the move. You can select these checkboxes. You can also move in one direction, or you can move in one direction and then come back. It's bidirectional movements, such as like with a step, with a bidirection, it's going to go to positive step and then come back. So there's going to be like 2 steps in some sense. You can ask for, in some of the moves, you can ask for dwell after the move, see what happens after it does the move and then stops. And you can also do repetitive moves. And by the way, although the plot items ask you for what to show in your plot, this is just at the first stage. After you do any type of plots, provided that it's open, you can always look at its acceleration, following errors, whichever you like, and you can change it all the time. Because already all the data has been stored by the software. So you can always look whichever you want to look at. And these are typical moves like a step and a parabolic. And as you can see, for each of those, it's going to give you the peak magnitudes, peak time, overshoot, damping ratio, natural frequency, settling time, all those necessary stats so that you can compare different controllers easily. Also for the parabolic, it's going to show you the maximum following error around the move, the correlations with respect to following errors versus velocity correlations and acceleration correlations, which are actually quite useful in trying to find out your feed-forward gains. So here's one of the good things about Power PMAC. So for simple systems where you don't have any flexibility, then a PID will suffice. No issues, PID plus feed forwards. But what if you have multiple resonances? Then you can go to the filter calculator. And this basically allows you to specify what type of filter you want to implement. Such as you may need only one notch to attenuate one of the resonances. Maybe you have two resonances, so you may need a double notch. Or you have a notch, you have a resonance at, let's say, 200 or 300 hertz, but you have high frequency noise due to unmodeled dynamics or just quantization or the noise coming from the sensor. Then you can use a single notch plus a low pass. And you can also have a low pass. They are up to the fifth order Butterworth filters. And this tool, calculator, allows you to do just specify the filter frequencies in continuous time domain. It's going to discretize it for you by using bilinear transformation methods. And the good part is, as soon as you implement these filters, let's say you implement the filter, it's going to show you what type of filter is implemented on the information. And later on, like a couple of weeks later, you don't know what type of filter you implemented. Or somebody else come to the machine and try to understand what was done before. You don't need to know it, because as soon as you come up with the software, every information is stored inside Power PMAC. So even if you come with a different computer, it's going to grab all those information. And that information is going to allow the software to check first to show what type of filter it has. Was it a notch? Was it a fifth order low pass? And it's going to come up with that page for you. And in addition, it's going to also check the coefficients. Because maybe somebody else just downloaded some extra file. One of the coefficients is changed. So it's not the same filter anymore. And it's going to check for those also. So that's why it allows you to know everything about what type of filter implemented, what is the frequency of the filter, what is the damping ratio of the filter. All those things is going to be basically given to you all the time. And you can also use this filter coefficient filter calculator for the velocity loop also, the E polynomial. Okay. So this typically ends the tuning of your motor. The next feature that I want to talk about is actually quite useful, and it's already been implemented in the firmware, which we call as trajectory prefilter. Suppose, actually there's a really good demo over there to show how this works. But suppose, as a simple example, we have a really light robot arm, okay? And of course, it's being controlled by the wrist via the motor. As soon as you start to move really fast, you're going to see that the end vibrates due to the flexibility of the arm. So sometimes these frequencies are at really low frequency, like 10 hertz, 15 hertz. That there are two ways to do it. Either you can move it really, really slowly, okay? But for a pick and place robot, this is going to take too much time then. The throughput of your machine is going to be really low. But there's another idea. Why not try not to excite exactly that frequency? If you do that, you can still move fast, so you can have a really high bandwidth again, and you can use the move. Because the other way around is trying to notch it out in the feedback loop, which may not be possible. If it's around like 5 hertz, then if you want to put a notch at 5 hertz, then your control bandwidth should be like 2 hertz. You cannot go above that. You cannot put a notch, then it's going to become unstable. And for those cases, this prefilter is really useful. And there's some other more usages also. In some cases, the trajectory is coming from a CAM program or some other program which can be noisy. You can also use this prefilter to use it as a low pass to get rid of the high frequency noise in your reference trajectory. And over here, you can easily have this is a fourth order filter. You can easily have 2 notches, so you can actually attenuate 2 resonances. You can have 1 notch and a low pass, or you can have 2 low pass filters. And here's how, you don't need to worry about this, but here how is it implemented in firmware. And the reason why it's been implemented is in this way. For those of you who knows a little bit about control theory, this part makes sure that the steady state reference trajectory is always the same as the first one. Do you know what is Z? 1 minus Z to the minus 1? It's a delay operator, basically. In Z domain. So basically it looks like this: R of K minus R of K minus 1, which is the velocity, or close to velocity, the position difference. If I divide by the sampling time, it's going to give you the real velocity. But don't worry about this part, because the calculator takes care of it for you. You just need to specify the filter properties. And as an example, if I put a notch filter at 10 hertz, of course, it's going to do is it's going to just get rid of or attenuate the 10 hertz signal in your trajectory. And as I said, you can see a really good control demo over there, how it works. So probably it's, it's actually, this one was quite useful for us for an interesting project. We were at one of the biggest semiconductor machine builders, Tokyo Electron. And there was a mechanism which is used for wafer inspection machine. And it's a mechanism like there's 2 motors, 2 connected links, and on top of that, there's a small guide so that it moves this way. So as soon as you rotate this way, it's going to go up, go to one station, and then it's going to come back, rotate, go to the other station, something like that. But they have the problem. They have huge when you move it, they need to move some at really high speeds. And there was a huge acceleration in Z. Although it doesn't seem that they're coupled, due to the fact that there's a guide rod over here, the accelerations actually creates a resonance here. And it starts shaking like more than 500 milli-Gs. And they have some specs for that. They need to do it like less than 50. Actually, we did it. We used trajectory prefilter. Find out that frequencies from the accelerometer they have on Z. Look at the X and Y accelerations also. Do a prefilter. Actually, we used like 2 notches. And the vibration was down to less than 50 milli-Gs. That was like 1 to 10. They were really impressed with that. But in the beginning, we thought that, okay, but this doesn't make sense physically, why they're coupled that way. Was it the bending? Because it's when it goes up, it's like a big plate. Maybe it was the bending. Then we thought that we can't do nothing with that because there's no actuator here. But here's a simple test to understand if it works or not. If you move it slower, if the vibrations are less, then yeah, the trajectory does something. Without even going to modeling the system, you can understand how it works. So another thing that's what is important is I'm going to talk about the new feature, which is also built in the firmware. It's a servo algorithm. Actually, what we call is Gantry cross coupling. And here's the idea behind it. Let's say you have 2 Gantry motors. Typically, they of course have a bridge between them, and you're moving the Gantry. If one of them has more load on it, then what's going to happen is, although you won't see it by eye, it's going to basically, they're going to be trying to bend the bridge between them. And if it's too much, you can break it. So the Gantry, standard Gantry, so let's say you specify your Gantry follower and the leader, both of them are going to be working on their same reference trajectory. However, they're going to be completely independent in terms of their servo. So that's why they are completely independent in terms of doing it. So one way to try to minimize the skew between these 2 motors is to couple them. And that's what is called cross-coupled Gantry control. And you can see that this structure shows how it's done. So on top of the standard servo algorithms running on these motors, the algorithm checks for the following area in between these 2 motors. And we have PID terms to compensate for them. Okay? So this way they are coupled, and that's why you can actually you can minimize the skew while you're doing a move. And there will be less stress on the bridges, of course. Most of the time, what I call the following error between these 2 errors is called Gantry following error. It's going to decrease it by half, 1/3 with the addition of it. And of course, if there's any disturbance, without this, these Gantry motors are not coupled, so they are completely independent. So you can, this always helps to minimize the skew with any moves. And how the software helps to tune these. So as soon as you specify your motors as Gantry form, such as my motor number 1 is my Gantry leader, and the Gantry follower has to be always the next consecutive motor. This is how the algorithm is written. So it has to be the next motor. Motor 2 is your follower. As soon as this is set up, the software will know, oh, this is the Gantry leader, motor number 1. And if you go to motor number 2, it's going to show this is Gantry follower, and it's not going to allow you to do any type of move from the Gantry follower motor. And here, when it shows this, when you go to the Advanced Auto-Tune menu, you're going to see a checkbox here. If you don't check this box, if you do Auto-Tune move, by the way, the Gantry Auto-Tune is going to move both motors at the same time, so you don't need to do one once and twice. So it's going to come up both identification routine and then come up with the gains for you. And if you select the cross-coupled Gantry control, it's going to also come up with the cross-coupled Gantry gains for you. And of course, later on, you can fine-tune it when you go to interactive tuning by going to set Gantry cross-coupling gains, so you can change them later on. And you can put your proportional and derivative and integral gain for both motors. So it's two sets of gains. And one more feature we added is what I call a simple auto-tune. If you remember from the advanced auto-tune, you have to specify the excitation settings. You have to specify the desired natural frequency damping ratio. In this one, we try to make life a little bit simpler for the end user. The only thing that we ask for is, because this may change with respect to your encoder resolution, we only ask for the minimum travel and the maximum travel. That's allowed. And by just simply, with this dial, you can have a slow and robust or a fast and aggressive movements. One dial. You do the auto-tune. The difference between this and the other is this is going to be an iterative style estimation algorithm. And it's going to do several auto-tune moves. And there's a stopping criteria. There's a logic behind it. And it's going to come up with the gains, everything for you, so you don't need to specify the damping ratio and all those things. And same thing for current loop tuning. Same idea. Actually, this one is much more simpler. There's only one dial. So you just select the performance. Just start iteration. So it's going to do, again, an iterative style identification algorithm on the current loop properties. Okay? This is probably much more easier than that. And after all these, we have one more extra feature that we added that I wrote. This is like an adaptive control algorithm. And this is useful when you have, this is useful for basically, this has to be close to a rigid body system. So if you have flexibilities, this is not going to work. But what this adaptive control algorithm does is, if you guys heard about it, there are actually two types of adaptive laws. One is called model reference adaptive, and the other is called self-tuning adaptive controls. Actually, this is more closely related to self-tuning controllers. And what we do is, as soon as if there's a movement, and if the load changes, then the overall gain is going to change. By estimating that gain inside the servo routine, I can actually change my control gains so that I will have the same performance no matter what happens. So if you don't know beforehand the load changes, this is the tool to use. But let's say if you know it, then of course you can use what we call gain scheduled adaptive control. If you know, let's say, if you're changing the tooltip for a robot and it has different loads, then you can change your gains accordingly, because you know when you grab that end tool. And you can easily set this one up. And you'll see actually there's one more extra thing in your, if they updated your IDEs, you will also see gain scheduled adaptive control. But let me just first talk about adaptation, how you set up this adaptive control. So the only thing we need to know is the nominal plant gain, and this can easily set as soon as you do auto-tune move with your nominal loads. It's going to set this gain for you actually. So one other way of finding this one is with the regular loads, you can do an auto-tune move and you can come up with the nominal plant gain and specify this. There are four more parameters to set it up. Estimation min DAC is basically, here's how it works. So to find out that gain inside the servo routine, there's a least square estimation method to find that gain. So we look at the accelerations and we look at the inputs, so we can come up with that gain all the time. But there's a least square estimation method in terms of some window size. And the estimation time, actually, that gives you the estimation window size. So how many datas that are used to come up with that gain. The estimation min DAC is useful because sometimes you have really low inputs. So your signal to noise ratio is really low. So that won't give you a good estimation. By setting this thing to, let's say, 200 DAC bits, 100 DAC bits, the inputs below that range are not used in the estimation or in the least square estimation law. That's the idea. So it's like it's basically acts like a low pass filter in some sense. And there are two more things that you can set it up, and these are called minimum inertia and the maximum inertia ratio. Here's the idea behind this. If you had any background in adaptive control theory, there's something called parameter drifts. Adaptive controllers are nonlinear controllers, and sometimes, let's say, you try to come up with the mass of the robots. The algorithm will run good, but then one of the parameters will try drifting, especially if you don't have a rich signal. So if you're not forcing, if you don't have a really good signal so that your estimation works. And the parameter will drift, and after a while it's going to just run away. It's going to go unstable. So the same thing, to prevent happening that thing, this basically sets a saturation limit for the estimated gains. So this algorithm will never go to unstable because of these. Otherwise it may go unstable. You can come up with a negative gain. And then of course then it's going to be reversed. So that doesn't allow you to do that. So this is like a safety feature for you. And these tools basically will show you what happens when there's an estimated gains changes. At each servo cycle, it's going to update it to show it what's going on. And in this slide, we don't have it, but there's one more, a slight variation of this adaptive control law. One of our customers wanted something like this. When you have the maximum inertia, like this, this adaptation will make sure that your bandwidths, no matter how your load changes, is going to stay the same with the same damping ratio. But they want this something a little bit different. So, okay, I want at max inertia, I want this type of, let's say, I want 10 hertz bandwidth. With really low inertia, where your gain is high, I want like 40 hertz bandwidth. With some damping ratio. Still, it's going to be similar. The estimation algorithm is going to be the same. But what I do is I change linearly when the gain changes. Let's say if I'm in nominal gain, then the bandwidth is going to be around, let's say, 10, 40, 25 hertz. So it's going to basically linearly change the bandwidth and the damping ratios around these stats. That's why we call it like gain. It's not gain scheduled adaptive control in some sense, because it basically changes linearly with respect to your estimated gain. And it has also a setup page similar to this, but instead of nominal and nominal gain, you basically ask for minimum gain, maximum gain, and it asks for what are the desired bandwidth and the damping ratios for those endpoints. And the last thing that I want to talk about before going to iterative learning control, because it's not there yet, but I want to talk about this interactive filter. And this is, you can use filter calculator anytime, but this is what some of our application engineers wanted, especially when they're tuning the machine, let's say for a notch. They can come up with the FFT and look at, let's say, they find that they have a resonance around 250-55 Hertz. Okay. Here's one thing to do. They can go to filter calculator, put like 250 Hertz, look at the noise, because as soon as you put the notch, you're going to see that noise is going to be eliminated and do a move. And then come back and then change it to 251, 252 to find the perfect spots. For those, they wanted something like this. So as soon as you change the dial and stop the mouse, it's going to directly implement on the fly the filter coefficients. So this way they can find the exact frequency in a really simple way. So that was the idea behind it. Of course, you have to be careful. That's why we ask for, make it sure that this is for advanced user. If you set this dial too low, for example, for the low pass, you can make the system unstable. But that's the main idea behind it. And the last thing that it's not here, but it's going to be there, is what we call a iterative control. Hopefully in the next release, it's going to be, right now it's actually being implemented for CAM tables. And it's called CAM iterative control. And the idea behind is actually quite simple. If you heard about iterative learning control, as soon as you have a cyclic motion, such as like a CAM, it also repeats itself. And there's always disturbances that you don't know much about it. But if I'm going through each cycle over and over again, we actually define our CAM tables in terms of zones. So you give the zones, you just give the points, and in between there's a third order interpolation between the trajectory. So at each zone, so it's like a special learning control law. You can find, let's say I'm in the first iteration. I know the following error. And in the next iteration, I can add on top of our control law, I can add this with a learning gain, multiply this error, and add on top of my servo. This way, in an iterative fashion, in the cyclic fashion, it actually acts like an integral action. And it's going to try to minimize those following errors when you go on through iterations. That's the idea. And we're going to also, I'm actually implemented for the compensation tables also, 1D torque compensation, because it's the same idea. If you're doing the same trajectory over and over repetitively, and it's going to work for that. Right now, it's already there inside the firmware, and there's the software how to set it up from the software side. And hopefully for the next release, it's going to be also allowed for the comp tables, because it's the same idea.